since we ended with the very last thing we wrote was plug it in when it works, let's make ourselves a little list of how to find a limit or how to compute a limit. That'll sound more like we're calculus people. How to compute a limit. And this is just kind of a little guideline. It's not necessarily a detailed, it's not like, oh, we're done now. I have this screen. Can you just sit down and let me try a few? It's more of a, so you'll understand the process you should go through, okay? Just like if I gave you a quadratic equation to solve, I would be devastated if your first instinct is to use the quadratic formula, because your first instinct should be to factor something, right? So it's the same sort of thing. So I'm going to try to give you a start off of where you're going to go with that. So option one, the thing you want to try first, and of course, if it always worked, there wouldn't be a 2 and 3, right? Plug in the x value. And when you plug in the x value, the y value is your limit. And we'll talk more about that in the context of examples. So that's your first choice. Your second choice will typically be to simplify the expression, in other words, the expression you're trying to find the limit of, algebraically.
Teachers, please call. Excuse me. Please.
It was funny, Fritz. Come on, laugh. Okay. Now, neither one of those sounds terribly scary because they sound like things you've done before, right? Okay. But I'm going to go ahead and tell you 3, and this is sort of your backup plan. No, I'm actually going to insert a different 3, and then it will be 4 that you're like, what? And we'll get there. All right. The third thing I'm going to suggest is that you graph on your calculator and use the table. Now, just like when we did the sin x over x yesterday, if you do that, if you try the third option there, what may well happen is that if you have, and most people typically have your delta x in your table set up at 1, you wouldn't have been able to tell from yesterday. Because what would have happened if we just left our delta x at 1? At -1, we would have had a value. And then what would have happened? Then it would have jumped right to the error for 0, right? So you wouldn't have seen what was the transitional change from that value to the error, and that's what you want to see. All right. The fourth option is the sandwich theorem. I knew Mackie would have something to say about the sandwich theorem. I just knew it. And the sandwich theorem is actually where we're going to end up today. You thought what? Nope, that is the universal nickname for it, and you'll see why. Yes, that'll be the last thing in our notes, which we only have a couple more things before that, but that'll be the end of the notes, and then we'll do examples, okay? And you'll see why it's called the sandwich theorem. And it's a fairly simple idea, but it's also one that students have a hard time connecting with. So that's okay. There will be a lot we do in here that takes time for it to kind of click, or it makes sense to you at some point for whatever reason. All right. How did we decide yesterday with sin x over x that the limit as x approaches 0 of that function is 1? How did we decide that the limit as x approaches 0 of sin x over x is 1? How did we decide that? Okay. We graphed the function, went to the table, reset it, started at -1, changed our delta x to 0.1, and then what did we do? You said trace, but we went down the table till we got to 0, right? And watched what happened to the y values. Yes. And then what did we do? Didn't we start at -1? We went from -1 to 0, and then we went from 1 to 0, right? So we looked at it on both sides. For the limit to exist, it has to be the same on both sides. Okay? So when we say the limit, and I'm emphasizing the word the there, when we're in conversation or you see that written, if you are given that the limit as x approaches whatever of some function is some number, that is telling you that that is the limit. That is that the limit is the same from the left and the right. Okay? And we'll continue to talk more about that too. All right? But there is the possibility of one-sided limits. Because there was an example, I'm going to see if y'all can remember this.
Wait, is this under the sandwich theorem?
No. No, I'll let you know. I'll put a heading up for sandwich theorem. One-sided limits. Remember yesterday we talked about how we knew before we ever graphed it. Well, first of all, let me rather than saying remember we talked about it, let me ask you again. How do you know when you look at sin x over x that there's going to be a problem at 0? Because you have an x in the denominator. And in a lot of functions, especially when it's, a typical rational function with something algebraic in the top and the x thing in the bottom, we expect there to be a what? Where the bottom is 0. An asymptote, right? But when you start throwing in sin x and other types of functions, you're going to not necessarily get a result that's expected. All right? Remember when we were talking about the discontinuities? What are the types? There's a whole, which is what we found in sin x over x, right? The jump and the asymptote, right? Okay. Well, think about those 3 discontinuities and talk to me about why it makes sense that for sin x, and because I remember I drew the little sketches of the segments with the dot and said what happens here and here and here. Why does it make sense for sin x that there is a hole that, remember the graph doesn't show you, but we figured out that it was there. Why does it make sense that there's a limit there? No, don't tell me analytically. Tell me from the graph perspective, from what we just said. We've already talked about it. Y'all are going analytically again. I'm saying when we traced it, how did we figure out that there was a limit? Because it came to the same spot from both sides, right? And okay, that's kind of where I was trying to get you to go. Now, talk to me about a let's say a vertical asymptote. What's going to happen at a vertical asymptote? What is the graph going to do when it gets there? It's going to shoot either straight up or straight down, right? And there are multiple possibilities there, right? From both sides, it could shoot straight up. From both. I don't know what we lost there.
Wait, Mrs.
Yes.
So like on that one, like there is like no like the limit, like that doesn't even.
Right. Exactly. The limit doesn't exist at the point, but that's why we have to talk about one-sided limits.
Okay, so like there's a limit. So could there be like 2 limits?
Yes. But you would specify the limit from the left and the limit from the right. Okay? All right, and here's what this looks like. So let's start with the right hand just because they did in the book. And that's how we refer to it. We refer to these 2 one-sided limit possibilities as the left-hand limit and the right-hand limit. Okay? And this one, the limit as x approaches c. I was going to say, I thought I was losing my mind. I glanced down and my allergy eyes saw a minus sign there. I don't know, but I take all kinds of sinus stuff and I still wake up with my right eye crying at certain times of the year, and this is one of those times. Does this notation look familiar?
Yes.
Didn't we talk about this last year? What does that mean?
As it approaches.
That's right. The limit as x approaches c from the right. Yes? Okay. Of the function. I need to unlock my door. Let me pause this thing. Okay, we are recording again. The right-hand limit is written as you see here. So it is the right-hand limit because, and this is what's going to be weird. Because if I'm approaching, and let me draw a little picture here for you. Let's say that we have this function, and I want to know what the limit is, and I'm just going to pick a random spot on it, so it doesn't even matter, right? Well, when I'm approaching that point from the right, how do I have to move? How did we move on our table yesterday? It was backwards, wasn't it? And what is backwards in the coordinate plane? to the left, yes? So you're moving to the left, but you're coming from the right, so it's called the right-hand limit, okay? And for some students, that gets confusing. For other students, it's just like, well, that makes perfect sense, so I'm not going to argue with it, okay? So this is the limit as x approaches c, the x value of interest, from the right side of our function. That's what that means. Everybody good with that? Okay. Obviously, if there's a right hand, there has to be a left hand. What will be the difference in the notation? That's right. We'll have a little negative sign there. So the limit as x approaches c from the left of f of x. Same thing. So when it's called the left-hand limit because I'm coming from the left, but I am moving to the right. Does that make sense? Okay. And hopefully by way of examples, this will be clearer. All right. So we want to write what we've been talking about for a couple of minutes here. That is, and I want you to put the in all caps to emphasize it. The limit only exists when, let's write it with the new notation we just learned. Because what did we say the limit is? And we've been kind of talking around this for a couple of minutes. That's right, when they're the same thing. So if I write the limit as x approaches c from the right of f of x, and I write equals, so this is the continuation of our sentence. The limit only exists, and I put the in all caps because the limit only exists when the limit as x approaches c from the right of the function equals.
The limit as x approaches c from the left.
Perfect. The limit as x approaches c from the left of that function. And the way we will say that when we're discussing problems is we will say the only time the limit
Teachers,
exists.
please send student 601 to...
Okay, so I would never do that. I would never do that to Clemson fans. I would never do that.
That's how they talk about Carolina.
Okay, don't even tell me Clemson fans don't talk trash. What?
Yeah,
I'm a
we do.
Clemson fan. I want Carolina to win because they're still representing South Carolina.
I just want any South Carolina team to win.
I hate it when Carolina fans or Clemson fans like don't cheer for each other like the other team if they're playing someone else. I hate
The only thing is I want Georgia to win Saturday.
That's because they're SEC, which I
Yeah.
understand.
But if y'all playing like
Yeah.
Boston College.
Yeah.
Your book talks about a two-sided limit, but we won't really talk about that. And the reason we won't talk about the two-sided limit is that it just makes more sense to understand the distinction between the limit, the left-hand limit, and the right-hand limit. That's the three that you want to have straight in your head. Yes?
Have scissors that I can use.
Yes?
I have this like really weird screen just chilling.
It's in the little pencil cup on my card if you want to grab
It's
that.
gonna bother.
Okay. And I sort of got ahead of myself by writing that because the next thing we want to write before we get to the sandwich theorem, and we wrap this lesson up and give y'all some time to practice after some examples. Theorem 3 is about one-sided and two-sided limits. And this is not only a fact to know, as we just wrote it in user-friendly form, and I'll kind of make this theorem in user-friendly form. And I'm going to cut out the part that it says a function f of x, because if I write f of x, what is that? A function, so it's a bit redundant. F of x has a limit as x approaches c. We're writing this in words. Oops. If and only if, and the universal way to write that is an if with two f's. Should have learned that in geometry. If and only if the left and right hand limits are equal. pretty much. But I'm going to take it one step further just again to kind of get you comfortable with symbolic notation and to fill in any gaps you might have from, say, your geometry class that may or may not have stuck with you and or was not emphasized enough at that time. The limit as x approaches c, and if I have no little symbol there, what am I talking about? The limit of the function equals capital L, and that's what you'll typically see is they'll refer to statements like this where they're referring to the limit itself. They'll use a capital L, M, or N, depending on how many functions they're talking about at once. Okay, now this is the notational piece I wanted to talk about. When you see an arrow with a head pointing in opposite directions, what does that mean? That what kind of implication? Right. One implies the other. They imply each other. There's not one that takes priority over the other. Okay? This implies that, now I'm going to start it and y'all should be able to tell me even without looking at the book. The limit as x approaches c from the right of the function equals, that's right. The limit as x approaches c from the left. And they use an and in the book, but I'm just going to go with that because this is the way you need to remember it.
It's supposed to be on the other side of the arrow, right? We just didn't have it.
Yes. It's like a sentence. When you're writing mathematically, even in symbols, whatever's on the last thing I write there leads to the next thing unless I stop it. Okay? So that takes care of it. They must be equal, and they must be equal to what? L. Doesn't that make sense? All right, sandwich theorem. We ready? All right. Now, when will we use the sandwich theorem? That's right. We have no other choice, okay? Now, most of what we do in this class, the sandwich theorem is something you should use probably when the book tells you to, okay? But was it, Becca, was it you that said the last resort? Or was it? Yeah, the last resort. That's your last choice, okay? I've never met a student who's like, oh my God, I love the sandwich theorem. I'm just going to use it for everything. Okay? So you're not expected to. And in your book, it is called Theorem 4, but we will put its name up here because this is the actual name of the theorem. It's not even a nickname. It is the name of the theorem. And you will understand why when I explain this to you, okay? When we have two functions that we don't have a way, like for instance, when I try to plug in the number I'm approaching, I get 0 over 0 or something over 0. Anything over 0 basically is a good example. Then clearly plugging it in did not work, right? Because I didn't get a limit. Does that make sense? All right. Well, then I look at it, and there's no algebra I can do to it because maybe the top is e to the x and the bottom is sine x. There's no algebra there, right? You with me? Okay, so that doesn't work. And if I can't use my calculator, or maybe if this was a homework problem and you were told to use the sandwich theorem to show that the limit is whatever it is, then that step 3 that I gave you as your option would be to get your calculator out, play with the tables, figure out what the limit has to be, because that might guide your thinking to how the sandwich theorem would apply. Okay? So what the sandwich theorem says, that now I'm going to write this out symbolically and try not to read it to you too much, okay? And I want to pause after I write the first little if bit, then when I draw the picture this will make sense, okay? So if f of x is less than or equal to, and I just want to go in the same order that they did. Oh, and I didn't. I already did not do that, so let me fix that. They started with g of x, just so you'll see that this is, I'm not making up my own theorem here. All right, so g of x is less than or equal to f of x. I should have thought about the fact that the f of x should have been in the middle. Is less than or equal to h of x. Pause. What does that mean? Graphically speaking, because you want to think graphically for this to make sense.
Like function A is less than.
Did you say function A?
Well,
I want you to literally translate what I just wrote.
Function G is less than function F.
Okay, but tell me graphically. I read that to you. Don't tell me what I just said. Tell me what that means. So if I like suddenly went to the next screen and there was a picture there, what do you expect to see?
The one.
Like G is below F, which is below H, right? Okay. So that's the if. What does that mean? from back in when you did conditional statements in geometry. And then I can't get the then if I don't get the if, right? So if you're having to use the sandwich theorem, then you're going to be given the f function, and you've got to think of a g and an h function that would work. Does that make sense? Okay? So if g of x is less than or equal to f of x is less than or equal to h of x, for all x not equal to c, let's pause and talk about what that means.
Like the whole.
You can't plug C in.
Well, everywhere, so what I'm looking at is everywhere but c so far, based on what we've read. Does that make sense? So it's okay if they're equal at c. Because that's the other thing you start thinking, wait, is that all right? Am I allowed to do that? Yes. It's okay if it's equal at c. Then, and oh, I don't want to leave this part out because this is what really matters, because this is what makes this so powerful. And you don't see this sounds like really vague wording, but it's actually really powerful. In some interval about c, comma, and we'll pause there. Okay? What does that mean, in some interval? Now you need to be thinking like we're in an English class, not like you're a mathematician. What if I say, as long as it works in some interval?
Like if C was negative, it would have to be as long as it works.
Okay, does the phrase in some interval specify any requirement as to the maximum or minimum size of the interval? Which is really awesome, because if you have two functions that go all over the place, but you happen to know at 0 what they do there, and they meet that sequential requirement that g is less than f is less than h, you can use it, even if beyond like 0.1 on either direction they change places, because you know how functions can cross and one's above here and below there, that kind of thing. It's okay as long in the neighborhood that you're on, you can make it work. Okay, so that's the power of that piece of that, okay? It doesn't have to be everywhere else, and that's a common mistake for students who are first applying this theorem, okay? And is our next word. The limit as x approaches c of g of x, and I'm going to keep reading so I don't mix these letters up on this Friday morning, equals the limit as x approaches c of h of x, and they both equal L. So talk to me about what that means. What is that first bit? The limit as x approaches c of g of x. What is that? So which function would I be looking at? The one on the bottom, okay? And as long as it approaches some limit, right? And h approaches the same limit. Can you guess where we're going without reading it out of the book?
Then they'll have the same for all
The
three.
S of X.
Right, and that's why it's called the sandwich theorem. So if I know one that is above and one that is below that have and I know their limit there for whatever reason, and that seems really abstract right now, but just trust me for a second. If I know that they both have a limit at that same at c, let's be specific, at c, what do I know about f of x? Where is it? In between them. Well, if it goes in between them there, what has to be true? It has to have that same limit. Now, the theorem itself says equals there, but sometimes it's helpful when you're applying the sandwich theorem, and I'll tell you this so that you can have an epiphany like Kayla Wallace had one day this week. She texted me, was like, oh my God, I finally understand the sandwich theorem. Because some students just wrestle with it, okay? But sometimes, once you know enough calculus and you think about it enough, it makes sense. But sometimes I can't get it equal there because it's too complicated a formula I don't know enough about, or function I don't know enough about it. But if I know that there's one that's below it by 1/10, the limit is, say, 8.1 for the one below it, and it's 10 for the one above it, and I know it's in between, I can at least say the limit of this function is between those two values. So you can even use it on like an interval kind of an approach too. So it's really kind of a cool thing to know how to do.
You don't write a picture. You don't draw a picture.
I am going to draw a picture. That's my next thing. Okay? So, but we haven't written the then, so let's write the then, and we'll do all this on this next screen. And I'm working on my the size of my writing, and if y'all want to see why it's varying all over the place up there, I'll show you how this works at some point. Then, because we didn't write then, right? Then the limit as x approaches c of f of x, what does it equal? L. Doesn't that make sense? Okay. Are we ready for the picture? Okay. I'm not going to put this in a coordinate plane or anything. We're just going to draw some curves and label them. So we'll start at the top. And what's the top function? H. All right, so get where I can do this whole screen kind of thing. All right, so let's say we have this function that's kind of wiggling around and it dips out right there, and we'll call that one H. So far, so good? And I'm going to put a point at the minimum of H, just to, so I'll emphasize it by making it a little bolder there. So I'm putting the points, and that's, what do you guess the x coordinate of that point is? C. Yes? This is where we're going, all right? And then from below, I have this function that peaks, coincidentally, at the same spot. Okay? And since this is the one that peaks from below, what is that? That's G. So for the sandwich theorem to apply, I've got to have this function H that F that I'm interested in that does what? Okay? And I'm going to do this intentionally, the way I'm going to do it, because, and then I want you to tell me why I do the picture this way, okay? So here comes F in between them, and it runs up and crosses H there, and then it dips down and crosses G here, and then it runs through the middle. Then it goes back up and crosses H and comes down and crosses G. That's my F.
It works.
It worked. Why does it work?
Because
Because all I need is some neighborhood. And it could be the kind of neighborhood, and you know how last year I showed you the importance of being able to take your calculator and just zoom and zoom and zoom until you see some particular attribute of a graph? You can think of it that way. Think of it as I'm on my calculator and I'm zooming to that spot. And sometimes when you're doing a sandwich theorem problem, it's helpful to graph them and zoom and zoom and zoom until you see it. But the window could be from point 0001 to point, give me a good example. What's just something slightly bigger than that. It could be almost like you need a microscope to see it. There's no rule that it has to be beyond that. Do you see what I'm saying? So that's what I want you to see here. So I can pick any neighborhood I want to, because in some instances, and the context will make this make sense, but in some instances, I'll know, well, this function never goes beyond this on this interval. So I know for a fact that between this number and this number, this order will always be there. Because what you don't want to have happen is that what is on the left of the point is the bottom function becomes the top function on the other side. You've picked the wrong function. Do you see what I'm saying? Because they've got to be completely. So where's the sandwich in this? The bread would be which two functions? H and G. Doesn't that make sense? So that's why it's called a sandwich theorem. All right, and the neighborhood that I want you to designate is just put kind of what looks like parentheses, like you're zooming in on that little spot. Now, of course, I could actually make that neighborhood bigger, because in math, kind of the larger area that your idea applies to, the more powerful it is. Then we could extend that until I got to those points of intersection where the middle function is run all over the other two. Do you see what I'm saying? Does that help?
Yes.
Cool, we're done. Let's do some examples.